By the way, in the old days, this quantity B was called the magnetic flux density. And H was called the magnetic field. Okay. But nowadays, people, at least in English, both are called magnetic field. Because if you think about it, magnetic flux density doesn't tell you anything, right? Because the integral of B field over a certain area is the flux, right? So the magnetic flux is defined in terms of B. And you use that to go back and call this quantity magnetic flux density is crazy. Okay? For that reason, B field is called the magnetic field. H field is also called magnetic field, but it's confusing, so people say, okay, which magnetic field are you talking about? And you say, okay, I'm talking about B field. I'm talking about H field. That's what people do. So this is another reminder. This is the old term which people don't use anymore because it's stupid. Okay? So if you did so, then you move ms to the other side. So magnetic susceptibility is G times mu sub B, according to this approximation. S plus 1 times M saturation. But M saturation is S times G mu B, right, divided by 3 kb T minus theta. Okay? If you look at this expression, you realize this is nothing but the so-called Curie's constant. You have seen when you're an undergraduate student for magnetic moments which do not interact with each other and place in a magnetic field. And in Curie's law of susceptibility, you have T. But instead of T, you have T minus theta. Okay? You got a question? Are you doing okay? And this quantity theta is called Weiss temperature in honor of the person, the theorist who studied magnetism and experimentally first observed that some magnetic materials at high temperature and low magnetic field has such a magnetic susceptibility. So now, so far, this is exactly what Professor Hosokoshi reviewed a week ago. And let me just continue. Now, if you look at the inverse of the magnetic susceptibility as a function of temperature, we're talking about high temperature regions. So low temperature regions in which the approximation, mean field approximation, will not hold. I'm going to use broken line. This is a Curie's law for non-interacting magnetic dipole moments. Now, when theta is positive, then the inverse will extrapolate to a positive intercept. This is the Curie-Weiss behavior with theta positive. Theta positive means J is positive. Which means it's a ferromagnet. Okay, magnetic dipole moments whose interactions are ferromagnetic. Now, if it's antiferromagnetic, then theta is negative. Therefore, inverse of this quantity will never become 0, but it will extrapolate to a negative intercept. This is the Curie-Weiss behavior with theta is negative, therefore J is negative. Therefore, this is the behavior of the system in which the interactions are antiferromagnetic. Magnetic dipole moments want to be antiferral to each other. Okay? Since let me see. I think this is a good point to stop and give you a quiz so that you won't fall asleep. Is that okay? Which one? I'm going to give you only 10 minutes. Therefore, why don't you do this? This one. This is easy, right? So, you know the definition of Brillouin function. We index x, s, at high temperature. Show that the this is g times mu sub b times s plus 1, 3kb t over b. Maybe you can derive this in 10 minutes, right? Of course, you have seen this when you're undergraduate students. So the quiz is show this is correct when the temperature is high, right? 10 minutes. Now, the point is, everybody can do this, but you give your answer using correct English. Don't just write down the equation and say, okay, put an arrow. Use words, right? Use words. Therefore, you put commas and periods and use words such as comma, where, blah, blah. Instead, we just write a bunch of equations with curly bracket and arrows. Okay? Okay, so I'll give you 10 minutes after my lecture. And let me continue, right? Before moving on to the low temperature behavior, let me point out a couple of things. So this is theta. This is also theta, depending on whether theta is negative or positive. Now, if you do exact calculation rather than a high temperature series, high temperature approximate, not high temperature, sorry, the mean field approximation, which is the lowest order approximation. Okay. Not only you do exact calculation at any temperature, not just high temperature, but also you abandon the mean field approximation and did the exact calculation. Or you may say, if you have an actual magnetic material, which is very well described by the exchange Hamiltonian, I have a look at in the beginning, then usually actual magnetic susceptible, inverse magnetic susceptible behaves in this way. If it's a ferromagnetic case, it usually comes like that. Okay. Inverse becomes 0 at the temperature, which is usually called T Curie, T sub C. And in antiferromagnetic case, this is the absolute value of theta. Before you reach that value, it usually deviates. And then that's something different. And this temperature is called T Néel. It's called Néel temperature. This temperature is called Curie temperature. And the important thing is the Néel temperature is usually less than the absolute value of the Weiss temperature, and as is the Curie temperature. Okay. Keeping that in mind, so this you can consider to be the exact calculation of the Hamiltonian, the susceptibility starting from the Hamiltonian or the behavior of a real material. We're going to focus on the low temperature. By low temperature, we are talking about temperatures which are lower or at these temperatures or lower than those temperatures.